Yeah. All right. Thanks to the organizers for the invitation. Very happy to be back. The last time I was here for a conference was before the pandemic, so many things have changed since then, but hopefully we'll get back to normalcy, and we're already getting there somewhat. So thanks all for showing up somewhat early in the day. Yeah, so what I'll be talking about is sort of a different perspective towards understanding some of these growth models or random metrics that we have seen quite a bit over this last few weeks. And this figures on the first slide will sort of become sort of somewhat clearer as we go on. So I wanted to use handwritten slides because that was easier for me to make figures. I'll also use the board sometimes. And again, the handwriting is not the best. So if you don't understand something, please stop me and then ask questions or make comments. Okay, so as this title says, I'm going to be talking about noise sensitivity and chaos in random planar geometry, and these terms will become clear soon. All right, so just to sort of set the stage, and we have seen this multiple times. So what we're talking about is sort of can be sort of thought of as a particular example in this broad paradigm of planar stochastic growth. It sort of encompasses a large class of models describing random height functions, interfaces with certain key features, which includes, let's say, a nonlinear slope-dependent speed, some global smoothing or surface tension, and then sort of the general growth is driven by local random forces. It turns out that as long as these sort of key features are present under rather general conditions, the models are expected to behave somewhat similarly. At least their fluctuation theory are supposed to be somewhat universal, and all of this falls in this paradigm of Corder, Percy, and Sang universality class, or as we know Newton by now, it's KPZ, and we'll be sort of focusing on one particular aspect of this. Okay, so this is the model of interest, and I don't want to define it again, but just to sort of briefly go through it so that we're all on the same page. So a particular class of examples of interest are random metric spaces where metric balls model random growth. All right, so all of these things are examples of stochastic growth, and one class of examples come from random metric spaces where you look at the metric ball around a particular point. As the radius of this ball increases, that sort of mimics random growth. And a particular example is FPP, or force passage percolation, where you put, let's say, random weights on the edges or the vertices of a lattice, and you randomly distort it. So the Z2 itself comes with a graph structure and has its induced L1 metric, but now let's say you randomly distort it. The way to do that, one sort of vanilla way of doing that is just put random weights on every edge, and that changes the length of each edge. And then somehow look at the induced shortest path metric. So here is set up a cartoon for that, and this was first introduced. This was first introduced in the 60s by Hammerlay I Welsh as a model of fluid flow. And for people who are somewhat new to this topic, this is sort of a great survey by Tuka, Michael, and Jack on somehow what the outstanding questions are, what the progress has been. Okay, so key observables are the passage time. So you take 2 points x and y. So txy is sort of the distance or the passage time in this random metric. And so that's a random quantity, so which we will denote by txy. And the more central geometric object is sort of the associated shortest path in this random metric, so which is the geodesic, which will be denoted by gamma of xy, right? And we have seen this multiple times, so it's just something that is very familiar to you by now. Okay, and the key difference from Euclidean geometry is the phenomenon of coalescence, where because each of these paths, so let's say you have 2 pairs of points, and the blue path is a geodesic between these 2 points, and the green path is the geodesic between these 2 points. They're both random paths trying to minimize their length. So they would tend towards the part of the space where the random variables are atypically low, and that would force them to sort of meet. And they would sort of continue their journey together and eventually bifurcate because their destinations are different, right? So that's sort of a key difference from Euclidean geometry where the geodesics are straight lines. So they either meet at a point, or they're the same, or they don't meet at all. Okay, and so as I was saying at the beginning, so this is sort of a simulation of a metric ball in an FPP setting. And so the different colors give you the different level sets. So points at a particular distance from the origin are colored the same. And as you can see that the limit shape is a sort of a convex body. And so the limit is supposed to actually depend on the exact nature of the distribution of the weights that you put on the edges. But now if you zoom in on the boundary, then you see some random function-ish kind of object. And the prediction is that this thing behaves universally, independent of what the edge distributions are, as long as they're somewhat nice, right? Okay, so but we will sort of take a slightly different perspective in this talk, and so this is sort of the perspective of energy landscape. So we can also view FPP as a random energy landscape indexed by paths. So each path, so the geodesic is the path with the shortest length, but you can take any path and compute it what its length is. And so now you can sort of look at a function which is indexed by paths, so the value of a function on a path is simply its length. Okay, that is what we will call as energy landscape, or the energy of a path. And the ground state is the state with the lowest energy, which in this case is the geodesic. All right. So every path has an energy, and the geodesic is the path of the smallest length, which is in physics terminology is the ground state. Okay. So we'll be interested in this phenomenon of multiple valleys. So this is sort of a cartoon of an energy landscape. Of course, the object that we care about is very high dimensional, but this should sort of at least convey some intuition. So if the model is a continuous model in the sense that let's say the edge weights are continuous random variables, then if you take any two fixed points, then the geodesic is unique almost surely. However, there will be multiple paths that are actually whose length is going to be very close to the geodesic. And so you should think of this as sort of an energy landscape, but this is the lowest point, which is the geodesic. However, you see that there are multiple points that are very close to the value of the geodesic. Okay, so these are somehow, as the picture depicts, this is somehow sort of shows existence of multiple valleys in this energy landscape. Okay, so we will be interested in sort of the geometry of this. Okay, so what are some of the questions that you can ask about the geometry of such landscapes? One would be to compute the number of such multiple values. There's a number of such values, and okay, of course, usually there are many of them. So the right way to formulate that is to compute the entropy of that, or compute the number at an exponential scale. Usually there will be exponentially many multiple values, and you want to compute, in some sense, the entropy of that. The other more geometric question is the relative positions of the multiple values. Like so here is a ground state. You want to understand how far or how different the location of another value is. Okay, so you have to sort of put some underlying metric on the space of paths. In this particular example, another sort of more maybe easy to understand example is, let's say, a matrix. Take a random matrix. In that case, let's say the first eigenvector is the ground state. And then you want to understand how many almost near orthogonal vectors are, whose quadratic form is close to the largest eigenvalue. Okay, so somehow the fact that this is near orthogonal means that these values are in completely different directions. Okay, so this is sort of some a typical question that people are also interested in. Any sort of questions at this point about what the basic goal is? Okay. All right. So and this sort of leads to sort of some pretty beautiful mathematics. So it turns out that in many sort of natural examples, the distribution of near ground states or these values describe interesting fractal properties or self-similar properties. If you look at where these things are located, they sort of exhibit nice clustering properties which are somewhat self-similar. And sort of an important consequence of existence of multiple values is this notion of chaos. What do you mean by that? So it means that, okay, so the ground state is the state with the lowest energy. However, if you now, let's say, port up the underlying noise a bit. So let's say if you're in FPP, you have all these edge variables that define the random metric. Now, let's say you port up these edge variables a little bit, then what will happen is that this will change the location of the ground state drastically. So if you port up the underlying noise a little bit, it will completely change the location of the geodesic, say, or whatever the ground state is in that setting. So this is what is known as disordered chaos, and physicists also consider port-upping other parameters. Let's say if you're in a positive temperature model, physicists have also studied situations where you port up the temperature a little bit. So you have some underlying temperature parameter, you port up that a little bit, and you see what is the effect of this change on the geometry of this underlying measure, right? So again, just to reiterate, so here is this energy landscape, here is the ground state, here are all these different values which are very close to the ground state. Now, let's say you port up the noise a little bit. What will happen is that, let's say this value will now become the new ground state, and this one will become a value instead. Okay, so the ground state will jump from one value to the other as the noise gets perturbed. And the point is, if you have many values in completely different directions, then the location of the new ground state is going to be in a completely different direction as well. Okay, Okay, so just some examples of energy landscapes that people have already studied. As I've already mentioned, the sort of an easy to state and somewhat easy to analyze example is coming from matrices. So given any random matrix or any matrix which is, let's say, symmetric, it induces a energy landscape on the sphere, on the unit sphere. So which is given by just a quadratic form. So the energy at a point at a vector z on the sphere is simply z transpose hc, where h is a random matrix. Okay, so now you given this matrix H, you have this landscape indexed by the sphere in the right dimension, and then the ground state is basically the vector with the largest quadratic form or the smallest. It's sort of symmetric. The definition is symmetric. Okay, so which in particular means that the largest eigenvector is sort of the ground state. Another example is, okay, so in this example, we looked at the energy on the sphere. So we allowed every possible vector z on the unit sphere. But often it turns out that if you restrict the vector z to the unit hypercube, then the discrete hypercube, then it turns out to be also an important model, which goes by the name of spin classes. The vanilla setting is the Sherrington-Kirkpatrick spin class, but you can also consider more general Hamiltonians. And again, here the quadratic form is the same. So this is the matrix. So sigma ij is the ijth entry of the matrix, which is, let's say, IID Gaussians up to symmetry. And then for any vector x in the hypercube, the energy is simply the quadratic form given by that vector. So it's exactly the same as the previous slide, but now I'm just restricting the energy to the discrete hypercube. Again, it turns out to be an independently interesting model. And okay, so so when I'm saying that you have to perturb the underlying noise, so one has to sort of define what that means. There are multiple models of perturbation. When the underlying noise is Gaussian, there is a natural way to perturb that. It's simply you evolve all the independent Gaussians independently along some stationary diffusion, which is, let's say, the Arjun limit flow. Okay, so for people who have not seen this in the past, it's not super important. It's basically for every t, I have a version of this Gaussian process, so that it's stationary. So for every t, the marginal is exactly the same. And this gives you the sort of joint distribution at 2 time points. So let's say the Gaussian process at time t has a decomposition as the Gaussian process at time 0 times e power minus t, plus some correction term to make it stationary, which is, and this Gaussian process is independent. So essentially the only thing that you should keep in mind is that this means that this is a stationary process whose correlation decays like exponential in t. Okay, so this is independent of this, and which means that the correlation of the time t process with the time 0 process is simply e power minus t. Okay, so it's a way to sort of evolve the Gaussians in a stationary way so that the correlation decays exponentially in time. Right? For discrete models, there are other natural notions of perturbation, but the result that will actually eventually formally state will be in the sort of Gaussian setting. Okay, so this is one canonical way to perturb the underlying Gaussian process. And so, okay, so what is known? So Chatterjee in 2009 showed that if you do this evolution of the underlying Gaussian entries of this random matrix, then if you look at the eigenvector, the largest eigenvector of this random matrix, so you see now you have a parameter t. So for every t, you have a largest eigenvector. And it turns out that the correlation of the overlap of the largest eigenvector at time 0 and the largest eigenvector at time t, so these are both unit vectors. They are both elements of the unit sphere. So their inner product is a number between -1 and 1. And turns out that if t is large enough, by large enough, I mean, if the matrix size is n and t is bigger than n to this number, okay, so this number will become more clear later, but for the moment, there is some number such that if t is bigger than that, which means that you have introduced enough noise in the system, then the two eigenvectors are essentially orthogonal. So the direction of the eigenvector at time 0 tells you nothing about the direction of the eigenvector at time t. Okay. And so this result was recently strengthened by the 3 authors, Charles Bardanave, Gabor Lugosi, and Nikita Zhivatovsky, who extended this result beyond Gaussian matrices to general Wigner matrices. Okay. And the point is, like, these things are doable because you have a lot of tools from random matrices that you can exploit. Okay, in the setting on spin classes, again, Chatterjee, when he initially introduced this theory, sort of made some progress, but then subsequently the results was improved significantly by, let's say, a group of authors like Jianding, Ronan Eldon, and Alex Zhai, and then more recently by Wei-Kuo Chen, using very refined understanding of the underlying spin class model. And the ground state was also shown to be chaotic in a group of, in this sort of paper of 3 authors, and more recently by Ronan Eldon in a more general setting. Okay, so the basic upshot of these 2 slides is when you're working with a spin class or a random matrix, you know enough about the model so that you can actually make these sort of assertions, right? Again, the precise nature of the results are not important. The actual result in this talk will be about a different model, which is FPP. Actually, not FPP, but a related one. Okay, and then the thing that probably started all this is sort of critical percolation. So again, I think this has been mentioned a few times over the duration of this conference. So again, for people who are not familiar, so let's say you take this the hexagonal lattice, and let's say every vortex is colored independently 0 or 1, or red and white with probability 1/2, which is a critical probability. And you're, let's say, interested in this random variable, which is, let's say, whether there is a crossing of open vortices from the left to the right. Okay, so that's an indicator function. I give you the coloring. X is either 1 or 0, depending on whether there's a crossing of red paths, red vortices from the left to the right. Okay, and again, so this is now a discrete model. There's no Gaussian anymore. Okay, so the dynamical model here is you simply you take this. Each vortex comes with a Bernoulli. It's a 0 or 1, depending on what the color is. Now let's say every vortex also has a Poisson clock. So whenever the clock rings, you simply refresh the Bernoulli. So at rate 1, every red becomes gets replaced by a new Bernoulli coin toss, which means it's equally likely to be both red or red or white. Okay, so that's the dynamical model here, and xt is the corresponding indicator at time t. So for every time, again, you have a Bernoulli percolation, and you want to understand whether there's a crossing at time t. And of interest is how is this random variable correlated? So xt is the status of this crossing at time t, and people care about correlation of this random variable as time progresses. And this was sort of initiated in this sort of famous paper of Benjamin, Nicolai, and Schramm, and then subsequently strengthened deeply by this group of 3 authors, Garbon, Pette, and Schramm, using sort of very complicated Fourier analysis on the Boolean hypercube. Okay, so this is basically what started sort of this study of dynamical models in statistical mechanics in some sense, at least in the mathematical literature. Okay, so again, so the point is all of these questions are extremely hard to answer for FPP, which is what this conference is about. And so we'll instead focus on a variant which enables the use of some integrable inputs which will allow us to actually answer some of these questions. Okay, but even for such models, only very recent developments actually allow us to pursue such questions. Like these questions are completely beyond reach, like even 5 years back. Okay, so again, this has been also maybe described multiple times, but just to sort of reiterate, so LPP is, okay, so there are various ways to set it. So I think it's sort of cleaner to look at if you do it in the vertical direction. So again, you have this square lattice, let's say, somewhat rotated. And now for every vortex, you put a random weight. And again, let's say you have 2 points X and Y, and then you look at paths which are oriented. So they only go up. Okay, unlike FPP, where you allow all paths, you only go up. And now instead of minimizing the length of a path, you maximize the length. Okay, so for every path which is oriented, you look at the sum of the random variables along that path, and you look at the one that maximizes the weight, right? And again, the point here being that if you now make some special choices for these random variables, then it turns out to have connections to random matrices, other algebraic objects that you can then exploit. Okay, again, I won't go too much into this because I think people have already seen this multiple times. Okay, but the formal result will actually be sort of stated for a model for which the understanding is perhaps the most refined at this stage, which is a sort of semi-discrete version of this. So again, this is something that showed up in in some form in Phil's talk, and so this is sort of a zero temperature version of that, where this is the noise is basically Brownian motion. So instead of having, in the previous slide, we had a discrete setting where we were putting random weights on the vortices. Now somehow the noise is given by independent Brownian motions on these levels. And all we want to do is take an oriented path which goes from, let's say, one point to another, and then just the energy of the path will be basically the sum of the Brownian increments along the path. Okay, so it's exactly a sort of semi-discrete analog of the discrete model that was stated in the previous slide. Okay, so any questions about the sort of, I'm not being super precise here, but at least things should be somewhat clear. No, so you have copies of the real line. So in this, so you should think of this. So here, both the 2 coordinates are discrete. Here you should think of this as being sort of continuous lines, and this as being sort of discrete. And then you can just take 2 real valued points on one level and another level, and just take paths of this kind where you sort of stay on this level for a bit, and then jump, and then stay on this level for a bit, and so on. And then for each level, you compute the Brownian increment of the corresponding Brownian motion, and then add them up. Any other questions? All right. So again, this is just to reiterate, if you sort of make transformations so that things are easier to look at, this is sort of a classical geodesic between 2 points. Ln is sort of the, let's say, the energy of the geodesic. It turns out that the energy grows linearly in n in the height, and the constant turns out to be 2 when it's Brownian motion. The fluctuation is given by n to the 1/3, which is one of these KP's exponents. So it turns out that if you center things properly and then scale it by the variance or the fluctuation, the limiting distribution is given by this Tracy-Widom, which again is not super important for this purpose of this talk. And then more importantly, or I mean, equally importantly at least, the transversal fluctuation. So if you look at this random path, the amount of deviation that it sort of undergoes in the horizontal direction is n to the 2/3. Okay, this is again some of these classical KP's exponents that you have seen multiple times. Right? Okay, good. So this is basically the triple of exponents which governs KPZ. One is sort of basically the scale of the system, which is this n. 1/3 is the fluctuation of the system, which is n to the 1/3, and 2/3 is essentially the spatial correlation length. All right. So and one more thing to keep in mind is now let's say if you look at this geodesic profile. So let's say you take this point here and then you compute the passage time or this last passage time as the other endpoint varies on this line. Okay. So then somehow the broad, so that's a random function, right? So I'm just plotting the passage time from this point to the end point varying on this line. It turns out globally to behave like a parabola. Okay, that's a deterministic function, but it's itself a random function. So what happens is you have some random perturbation on top of that. And turns out that this random perturbation is what is known as the Airy-2 process. It is stationary, and then it has some very nice properties like it's determinantal. It's also locally Brownian. So although the 1-point distribution is given by Tracy-Widom, the increments somehow behave like Brownian motion. Okay, so what you should think of is that the passage time profile looks like a parabola deterministically with some random perturbation on top of that, which is roughly locally Brownian. And that's not super surprising, the local Brownianity, because some of the underlying noise is very decorrelated, right? So everything is sort of IID in this definition. Okay, and another sort of thing to get out of the way is transversal fluctuations. As I said, it sort of happens at scale n to the 2/3, but then you can also have tail bounds. So the probability that you deviate by more than x times n to the 2/3 decays like e power minus x cubed. That's not super important, but again, many things are known for such models. Okay, so dynamical perturbation of the underlying noise. So again, I'll state the result in this semi-discrete setting, but for purposes of exposition or just sort of conveying intuition, it's sort of easier to talk about a discrete model. So again, let's go back to this discrete LPP model where you have vortices and random weights on vortices. And then let's say each weight gets replaced by a fresh sample and an independent sample at rate 1, exactly like what we did for critical percolation. So every vortex has a random weight. Whenever the clock rings, you just throw it out and then replace it by a fresh sample, okay? And so again, for every time, there is a passage time, and then there's a geodesic. I'm like, there might not be a unique geodesic, but you can look at, let's say, the leftmost one and things like that. But so let's say gamma nt and lnt are the geodesics and the corresponding weights or the energy at time t. Okay, so that's the notation. Okay, so what are the kind of questions? So the corresponding noise sensitivity question is, how does the correlation decay between the passage time at time 0 and the passage time at time t? Okay, so how much noise do you have to infuse into the system to sort of make these things roughly independent, right? So that's sort of the more analytical question. And as I said, so the last 2 decades have witnessed impressive progress in the study of noise sensitivity, pioneered by this paper of Benjamin Nicolai and Schramm, whose main motivation was to do this for critical percolation. And then also, besides being of interest in the physics community, a lot of the motivation also comes from computer science and algorithms. And so there are randomized algorithms that you can define based on sort of understanding of these models, on the noise sensitivity properties of these models. And such studies in the context of KPZ had already been present actually in the physics literature. So, but it's been a while. So it's been about 20 years since the first reference that I could find about predictions of noise sensitivity properties in this sort of setting goes, the one that I found was like early 2000s. However, only.
Shirshendu, what is the connection to algorithms? I mean,
yeah, so we can talk about that offline. And so, and it turns out that sort of only, as I said, like only now the mathematical understanding is sort of rich enough to be able to sort of try to make, for us to attempt to make some of these predictions sort of mathematically rigorous. Okay, so And then sort of, okay, so I sort of pose this noise sensitivity question. The corresponding chaos question is the following. So you take the geodesic gamma n 0 and gamma n t and look at their overlap. So these are two paths going from 0 to n. And so you want to understand how close or different they are. So what is a way to measure that? There might be multiple ways to measure that. One way to measure that is through the overlap function. So let's say these are discrete paths. They both have, let's say, n vertices on them. So you can compute the number of vertices that they share. Okay, so that's a number between 0 and n. So let's say we call that the overlap function, and that's a number between 0 and n. And so so two paths are somehow close if the overlap is close to n, right? So because they share most of the vertices, and if they're somewhat disjoint, then the overlap will be close to 0. Okay, so this is one way to quantify how similar or different the paths are. And so the corresponding question is how much, yeah.
You could not consider the thing that two paths, maybe in the second case, it means the two paths are at a distance of only one neighbor.
I'm like, so it might happen that they don't overlap at all, but they're still within distance 1.
Right.
But we say, yeah, we say that that means that the paths are different. Okay, and this is actually an important question. So we don't quite understand the geometry. Although we can understand this observable, it's not very easy to understand the distance in the Hausdorff metric or something. Okay, so again, so for the particular setting of the theorem, we'll be working with Brownian motion. And as you recall, when things are when the underlying things are Gaussian, you have this Arjun flow, which allows you to define the perturbation model. And although I defined it for discrete Gaussians, you can also define it for Brownian motion. So there is a way to construct an Arjun flow starting from any Gaussian process, in particular starting from Brownian motion. And so here is sort of this pictorial depiction of the perturbation. So here are the Brownian motions at time 0. You evolve them independently according to this OU flows, and these are the Brownian motions at time t. Okay? So that's the two noise systems that we'll hear about. Okay, is it broadly clear what the underlying perturbation mechanics is?
Each of them is an independent
copy. So these are Brownian motions which are independent. For each Brownian motion, forget everything else. Start an OU flow, which starts with this and is stationary. Okay, and so you have this independent diffusions, and you look at the status of those diffusions at time t, and you just plot them here. All right, so okay, so what are the sort of somewhat inroads into understanding this set of questions? So there are two key inputs. So one is Chatterjee's theory of harmonic analysis of Gaussian spaces. I'll describe some aspects of that. So it's not surprising that you need some amount of Fourier analysis, because also in the critical percolation setting, the thing that really gave them some handle on studying such questions was the Fourier analysis on the Boolean cube. So here you have to do sort of the Gaussian version of that. And then the second is, as I said, like sort of refined understanding of Brownian LPP, which is absent in other models. Okay, so we really make use of some very, very sharp understanding of how this model behaves. Okay, so this is the first formula, which might look a bit strange, but it's certainly quite powerful. And if I get time at the end, I'll describe how to derive this formula. So this is this sort of key input coming out of Fourier analysis is dynamical formula for variance. So recall ln0 is the passage time at time 0. So it turns out, and this was sort of developed by Chatterjee, is a general theory. So the variance of this passage time, okay, can be represented as an integral. And so you see that this representation connects the variance to the overlap. So this is O of gamma n 0 and gamma n s is the overlap between the geodesic at time 0 and time s. Okay, you take the expectation of that. So this is a random quantity, the overlap. You take the expectation. So that's a deterministic quantity. You take this integral of e power minus s times this expected overlap, and you integrate from 0 to infinity. It turns out to give you the variance. It's a pretty remarkable formula, but it's actually not very hard to derive. But we'll sort of use this formula for the moment, and at the end, we might discuss a bit of how to derive this. Okay, so but let's see what this yields. And also another consequence of sort of harmonic analysis is that this overlap function, the expected overlap function, is decreasing in S. Again, that's not very implausible, right? As you enter more noise into the system, the geodesics should become more disjoint, and some of the overlap should decrease. But this is a formal. This actually turns. I mean, like, of course, this is a random quantity, so that doesn't necessarily have to decrease, but the expectation decreases. Okay, so these are two inputs that comes out of sort of writing out the passage time in the Fourier basis and whatnot. But we'll sort of see how already this has some nice consequences, right? Okay, so let's see what the consequence is. So the variance is this integral of e power minus s times expectation of the overlap. And also more important, the expectation of the overlap is decreasing, right? So you can take this integral 0 to infinity, truncate it at t. So this inequality is true, right? So integral from 0 to infinity is exact equality. So this is bigger or equal to everything is non-negative. So this integral is bigger or equal to the integral from 0 to t. This integrand is decreasing. So you can replace this integrand by its time t value, right? So a lower bound for this integral is simply t times e power minus t times this expected overlap at time t, right? It's a very basic analysis given this formula. Right, so now let's see. So the variance of ln, as we have already seen from the KP's exponents, is n to the 2/3, right? And this is where the integrable nature of the model is being used. We know this bound. So, okay, so let's see. So this is bigger than or equal to t times, so ignore the e power minus t term for the moment. So t times expectation of the overlap. Now, if t is bigger than n to the minus 1/3, okay, so it turns out that the expected overlap is much, much smaller than n. So already from this dynamical formula for variance, it turns out that if you evolve this noise by time, which is more than n to the minus 1/3, the geodesic will start looking different. Extremely soft way of getting, in some sense, chaos beyond this time. Okay, I'm like, I don't want you to sort of look at this too closely, but the basic upshot is there's a very remarkable formula connecting the variance to the overlap, which already gives you low overlap for large times. Okay, so we'll see. All right, so using sort of similar strategy, it also turns out that if you look at the L2 distance between the passage time at time 0 and time t, you have a similar sort of formula. Okay, you don't have to look too closely at the formula, but it turns out that you can show that if t is now much, much smaller than n to the minus 1/3, then the L2 distance between the passage time at time 0 and time t is like less than n to the 2/3. So recall that the individual variances or the individual fluctuation of each of these quantities, these are both stationary, right? They have the same distribution. So their individual fluctuations are n to the 1/3 coming from this KPZ. So which basically means that you can upper bound this difference by roughly n to the 1/3 squared, which is n to the 2/3. But what it says is that now if t is small, then the difference is smaller. It's much smaller than what the KPZ exponent gives you. Okay, so what is the consequence of this? There are two consequences, one for large times, one for small times. So for large times, which we will call supercritical case, so the consequence of the dynamical formula for variance is that for t bigger than n to the minus 1/3, the overlap is small, okay? And also for t less than n to the minus 1/3, the correlation is high. So you have these two consequences. One is subcritical weight stability. The weight does not change too much if t is small. And the geodesic changes a lot if t is large. So these are the two sort of soft consequences of this remarkable formula, right? But you see that the two results are in for two different times, like one big large times and one small times, but they're about two different quantities. One is about the overlap, the other is about correlation. Okay, so it does not prove any theorem actually, because somehow it's sort of talking about two different quantities. Okay, so if you now want to prove a phase transition at time n to the minus 1/3, which is the time that keeps popping up, you have to prove one of these two things. You either prove that for t small, the geodesic stays the same, or you prove that for t large, the correlation decays, right? Because we've already shown that for t large, the geodesics are different, and for t small, the correlation is large. So you have to prove one of these two things to at least prove some transition happening at n to the minus 1/3. Is this basic sort of picture clear? So I sort of wrote down a formula, derived two easy consequences of that. They were about small times and large times, but about two different quantities. So they did not quite prove any theorem. And then to prove any theorem about a particular observable and transitioning from small to large times, you have to prove one of these two things. And they both turn out to be extremely difficult. And so what we did with Hammond a couple of years back is to prove one. Okay, so what we proved is that if t is much smaller than n to the minus 1/3, so there is some correction term which you should ignore at this point. It says that the overlap is macroscopic. So the dynamical formula for variance tells you that beyond t equal to n to the minus 1/3, the overlap is microscopic. Here we say it's macroscopic in n. Okay, so that at least proves that at n to the minus 1/3, you transition the geodesics transition from stability to chaos. Okay, and this was predicted, as I said, in the physics literature by these two people in 2004. But importantly, the other question, number 2, is open. So I don't know how to prove that the correlation decays beyond time n to the minus 1/3. And it has to do somewhat to the question that was asked, is that although I know that the geodesics overlap or don't overlap, I don't know their spatial location in some sense. Okay, so it's a basic state clear now. Like, so we know chaos happens, or there is a transition from stability to chaos in terms of the geodesic at time n to the minus 1/3, whereas the correlation problem is still open.
You have e power polynomial in n times log log.
No, n to the minus 1/3 is a polynomial in n.
No, that's the correction.
Yeah, n to the minus 1/3 is a polynomial in n. This is e power minus poly log log n, which is a subpolynomial factor.
Subpolynomial.
Yeah. So the polynomial dependence is this.
Right. E power is polynomial.
Poly log log. Okay, any questions? Okay, so here is sort of a simulation of that. This is sort of the subcritical picture where you see some overlap. Here, this is a supercritical picture where you see a lot of disjointness. Okay, so the red and the blue paths are the two-time geodesics. Okay. Okay, so why is t equal to n to the minus 1/3 critical? So what is it about this time? Okay, so we'll give you a heuristic, but the proof will actually not use that heuristic, but it's sort of somewhat easy to keep in mind and will drive some intuition. So again, so for heuristic purposes, let's again go back to a discrete model. So again, let's look at discrete LPP, where let's say the random variables are Bernoullis. And again, you go back to this dynamical model where each bit gets updated by at a rate 1%, along a rate 1% clock, right? Okay, so here is the geodesic gamma 0 at time 0. Okay, so let's see okay, so the claim is the transition happens at t equal to n to the minus 1/3. Okay, so first let's look at a shorter time. Let's say t equal to n to the minus 2/3, which is a much smaller time. Okay, so how many bits get updated on this path by this time? So the path has length n. The time is n to the minus 2/3 or slightly less than that. So the number of bits that get updated by this time is n times this time, which is n to the 1/3, or slightly smaller than that. Okay. So only but recall, so this is this statement that on each path less than n to the 1/3 many bits get updated. All right. Now recall that the fluctuation of the system, the length of this path itself fluctuates at scale n to the 1/3. Okay, so you're changing much fewer bits. So it essentially does not change the weight of this path at all by this time. All right. So this path, which was a geodesic at time 0, continues to be almost a geodesic at time t when t is this small. Right. Okay, so as I said, so the value of the path does not change much. So this path continues to be a near geodesic by this time. However, the claim transition happens at a later time, which is n to the minus 1/3. Okay, so at time n to the minus 1/3, the number of bits that get updated on the path is n to the 2/3 now. It's much larger than the fluctuation of the system. So the value of this path changes a lot. It changes by n to the 2/3. So that makes it completely hopelessly incompetitive. Okay. However, what happens is that the geodesic reroutes. So suppose I update this bit, so the value of it goes down. So what the geodesic will do, it will locally reroute to make up for this loss. Okay, so it will do this reroutings at every location that the bit gets updated. Okay. Now, maybe it's not very hard to maybe imagine this updates or this local reroutings are somewhat IID because they're happening in different parts of the space. So and the length of these excursions are not that big. So they're not very interacting. They're not interacting much with each other. So they're somewhat IID. So there is some global cancellation. So you see that there are n to the 2/3 many updates, which are all giving you some changes, local changes, which are acting in an IID fashion. So overall, there is some cancellation, which gives you a CLT effect. So in particular, the total net change by this reroutings will be square root of the number of updates, which is square root of n to the 2/3, which is n to the 1/3 that matches the order of the fluctuation of the system. So this somehow indicates why n to the minus, so you need to update n to the 2/3 many bits on this path to somehow infuse enough change so that it matches the global fluctuation of the system, which tells you that this is indeed the right location of the transition. This is completely heuristic. We cannot make any of this precise, but this is sort of what drives some intuition at least. Is this intuitive sort of description somewhat clear? Okay. Okay, the proof takes a rather different approach. And it's super complicated, so runs for about 200 pages. Okay, so all we have to show is that for times which are small, the geodesics sort of overlap. Okay, that's sort of the goal. Okay, suppose the overlap is not large. So the geodesics, so we want to prove that for small times, the two geodesics are rather similar. So we'll prove by contradiction. So let's pretend that they're not similar. So let's say the overlap is small. Then the excursions, so you look at the excursions between these two paths. So the excursions cover up most of the length, right? So they're not overlapping much. So there are excursions between these two paths that cover up most of the journey. Okay, so we'll sort of, for this purpose of the talk, we'll only describe one case where there's one large excursion. Okay, so I mean, there could be multiple different geometries of the two paths. So let's just look at this toy case where there's just one big excursion which accounts for all the non-overlapness, right? So recall again that there was this stability input that if t is small, so again, we are all in the small time regime, right? All we care about is the subcritical time, and we want to prove that the geodesics are similar. So we're proving things by contradiction. So let's pretend that they're different. So let's say they look like this. And also recall, but their energies are somewhat similar. This was one of the inputs from the harmonic analysis. So this weight stability input is crucial. So the blue and the red path, so okay, this picture is somewhat misleading. The blue path lives at time t. The red path lives at time 0. So although these are drawn on the same figure, they live on different time slices. Okay. And the harmonic analysis input tells you that their weights are somewhat close. Okay. However, it's sort of a problem that the two paths live in two different time slices. So it's easier to compare two paths if they live on the same slice. Okay. So it's easier to compare things at time 0, let's say. So this is sort of the key observation or the key sort of part of the proof. The key idea is to construct a proxy for the blue path, which now lives at time 0. Okay, so the blue path lives at time t. I want to construct a proxy for the blue path, which now lives at time 0, but shares all the features of the blue path. So it will have a similar weight. It will also have similar geometric features. Okay, so the proxy construction is sort of a key part of the proof. Okay, so how does the proxy construction go? So here's the blue path, which lives at time t. Okay, so throw some points on the blue path. And again, how you throw the points are important, but let's ignore that for the moment. And between these points, let's look at the best path at time 0. So the green path, so you take the blue path, put some points on the blue path, and then look at the green path is constructed as the time 0 geodesic between these points laid on the blue path. Okay, so each segment of this blue path between consecutive points is the time 0 geodesic between the corresponding points. Okay, so now we have sort of gone from a blue path which lives at time 0 to a green path which now lives at time, sorry, the blue path lives at time t. Now we have gone to a green path which lives at time 0. Okay, so now both the red and the green path, they both live on time 0. And that will sort of, and then we can sort of do some analysis in comparing them. Okay, so, but we want the green path and the blue path to be somewhat similar, right? So the whole point of constructing the proxy is that the green path should sort of retain the features of the blue path, but crucially now live at time 0. Okay, so the first feature that we want to ensure sort of persists is the weight. So we want to use the weight stability input. So recall the weight stability input says that if time is small, then the weight does not change much. So we'll use the weight stability input to argue that the blue and the green path should be close in weight. Okay. However, recall that the weight stability input was about deterministic points. It said that if you take two fixed points, then the weight between these 2 points at time 0 and at time t are similar. However, this is a completely random path. The blue path is a completely random path, and consequently, the points that I mark on the blue path are also random. So somehow what you have to do is you have to develop percolation theory techniques to use this deterministic result to develop uniform in space and time results. So that you can allow, so they're going to actually argue weight stability even when the endpoints are random. No. So it's sort of non-trivial. I'll at least indicate some thought, some of the sort of key sort of factors that go into the choices, but it's non-trivial. It's not. Yeah. Okay. So again, I don't have a lot of time, but just to sort of percolation theory. Okay. So I said like the weight stability was about deterministic points, but these are random points. So to be able to apply this, you need to develop some uniform in space and time version of that. Okay, here is one way to do that. So let's call a box good. If from every point on this side to every point on this side, the weight is stable. And it turns out that you can prove that each box is good with a high probability, and then argue that no path passes through too many bad boxes. So this is sort of a percolation type argument, which tells you that for most black points, the weight is going to be stable. Essentially, that's sort of the style of argument. Okay, so what is the upshot? So here, so again, it's sort of easy to develop this notation where tau is t times n to the 1/3. So recall that t is around n to the minus 1/3. So tau is a number which is much smaller than 1 now. It's somewhat cleaner to work with that. So from the weight stability, it says the weight of the blue and the red path are close. It's order tau to the 1/2. Tau is a very small number times n to the 1/3. N to the 1/3 is a fluctuation. So you can ignore that. Now we have constructed the green path, so we have to also compare the green and the blue. So you can also show that all this song and dance, you can show that the green and the blue path are also somehow close in weight. So overall, you get that the green and the blue path are close. Okay. So now you've constructed a proxy so that at least the weight is somewhat retained. Okay. And crucially, now they live on the same time zero slice. Okay. Now the next part of the task while constructing the proxy is to retain the geometric information. So recall that this transversal fluctuation results. So if you take any geodesic of scale m, then the fluctuation in the transversal direction is m to the 2/3. Okay, so here is sort of one way to sort of see so this goes back to Partson's question. So suppose the excursion, suppose the separation between the marked points is 2 to the m. Okay. So then the transversal fluctuation will tell you that the distance between the green and the blue path is 2 to the 2m/3. This is a consequence of this transversal fluctuation result. So which means that if the excursion size is 2 to the L, and if the points are laid down at separation 2 to the m for slightly smaller m, then see overall the geometry somehow is still, the excursion will be still preserved, right? So the initial excursion was of size 2 to the L. Now I've laid down some points at separations less than 2 to the L, and they don't fluctuate much by transversal fluctuation estimates. So this green path will also have an excursion with the red path of a similar size. Okay. Okay, good. So at least from, I'm like, okay, again, the choices are more complicated than somehow I'm letting on here. But broadly speaking, by this sort of, at least we have indicated how to sort of construct this green path so that the weight of the green path is similar to the weight of the blue path. The green path has a similar excursion structure with the red path as the blue path. But crucially, the green and the red path both are now on the time zero slice. Okay, yeah.
What's the
Yeah, so I'm like, as I said, I'm discussing a toy example, but there's just one large excursion. In the actual scale, in the actual sort of analysis, you have to do a multi-scale analysis because excursions can have all sorts of geometries.
So they could be vertical.
Yeah. So first of all, you can argue that if this excursion size is to the L, it's sort of unlikely that because both the paths are somehow geodesics, their separation will be also 2 to the 2L/3 in the other direction. So it's unlikely that this thing happens. So let's say this is a geodesic at time 0. And it's unlikely that this happens. It's an excursion, but the excursion, there is no overlap, but that's super unlikely. Because, and this is what the heading of the slide says, although I did not lead to that. Slender excursions are rare. So the excursions will be somewhat fat. Right, so, okay, so at least sort of we have some understanding of how to construct the green path. Any questions? Right. Okay, so all of this boils down in this toy case when there is one large excursion. All this tells us is now we have this red path, this is geodesic. We have constructed this green path whose separation is n to the 2/3 and whose weight is very close to the weight of the red path. Right? That's all that this is. Okay, now we have to rule this picture out. Okay, so how does one rule this out? Okay, recall that this was the passage time profile, right? If you take this point and then draw the passage time on this line, then it's a parabola plus some fluctuations. Okay, so this sort of a picture allows us to actually compute where the geodesic passes through, what this point is. Let's see how that is done. Okay, so now you do it from the two sides. Okay, so this picture tells you what the passage time profile is if you go from this point to this line. Now, as you can see in this figure, you can draw this middle line and draw this passage time profile from the two sides, from the 2 points. And that gives you a picture like this. So from the two sides, you have two parabolas, which are independent because now the parabolas are deterministic, but now now you have some fluctuation on top of that, which are independent because they depend on different parts of the noise space. Okay, so can somebody tell, okay, it's sort of not a good idea to ask questions. Okay, so Right. So given this picture, there's an easy way to compute where the geodesic passes through. Okay, so it's basically where the sum of these two random functions is maximized. Because this is the weight from this side, this is the weight from this side. The geodesic is the weight maximizing path. So it's essentially where the sum of the two weights is maximized. Okay, and so if you ignore the parabola for the moment, you have two Brownian motions whose sum is also Brownian motion. Roughly, I mean, these are not Brownian motions, these are area2 processes, but as I said, they're roughly Brownian locally. So now you have two Brownian-like objects whose sum is also like a Brownian object, the Brownian-like object. And the geodesic essentially passes through where this Brownian motion type object is maximized. Okay. So the geodesic passes to the point where the sort of sum of the two Brownian motions is maximized, and we all know that how a Brownian motion behaves around its maxima. It decays like a Bessel process, it diffusively decays away from the maxima. And so what does it mean? So you have this line, you have this, okay, so now it's not a red and green path, but a white and a blue path maybe, right? This is where the Brownian motion is maximized. This is where the geodesic passes through. And we also know that the blue path has weight which is close to the weight of the geodesic. That tells us that this Brownian motion, which is maximized here, is also close to its maximum value at this location, which is somewhat far away. And that's a Brownian computation that you can do to show that this is unlikely. So I won't go too much into that. So this tells us that the probability that you have a situation like this, where the green path is somewhat away from the red path macroscopically or on the right scale, but their weights are close to each other, by a Brownian computation, you can show that this probability goes to 0. Because we have at least ruled out this toy case after a lot of work. And again, as I said, this was just a heuristic overview when there is one single excursion. Okay. The actual proof is significantly more delicate. Needs to consider excursion of all sizes. For moderate excursions, one can still construct a proxy. If the excursions are not very large, but still somewhat large, you can construct the proxy. If the excursions are very small, the proxy construction breaks down. So you have to have a separate argument for small excursions. So that's essentially the talk. I have a few slides on sort of this Gaussian harmonic analysis and how to develop this dynamical formula for variance. But I think that I'm happy to, I don't think I have enough time to get into that, but I'm happy to stop here. And if people are interested, I'm happy to talk about that offline. I'll stop here.
Any questions for Shirshendu?
So what do you do for small excursions? Can you?
Yeah, so it turns out that suppose you have a situation like this. Okay, so this is a picture. So you can a priori prove that, okay, so you can a priori prove that any such path at time 0 will be much smaller than the weight of the white path. And then you can get a crude bound on how much the weight of this path can increase as you evolve the time. And so even then it's going to be hopelessly incompetitive at the later time. So that's basically the style of the argument. No, you don't. Yeah, because somehow the point is that these excursions are so small, so you cannot like retain the geometry feature when you sort of, because the green path incurs some error when you, and so the error are going to be fine only when the excursion is large enough. So if they are very small, the green path will completely like sort of erase all this sort of geometric information.
Thank you.
Christian?
Yeah, so it's expanding the, yeah, so here is maybe a way to see that. So
I was wondering what was meant by
so let's take
Gaussian
any
harmonic
function
analysis.
Yeah, let's take any function f of some, so let's say there are some underlying Gaussian variables. So take some function f of that, expand that in the Hermite polynomial basis, and then sort of analyze. So this is basically, and so now it's sort of, you want to study the coefficients, you want to study the eigenvalues of this expansion and things like that. So the Hermite polynomials form an eigenbasis of this, the generator of the Arjun process. And then you sort of expand f in this Fourier basis, and then you want to understand what these coefficients are. So that's essentially what the harmonic analysis means. And it turns out that there's a very nice formula, which I don't have on the slides, I think, is basically given the spectral expansion, you can define a probability measure. So this is cleaner in the Boolean setting, and it turns out that the expectation of the whatever that probability measure is actually governs the correlation decay when you infuse new noise in the system. So, so in some sense, although this is not entirely correct, so there is a new measure. So you see that alpha k. So from this equation, variance of f is summation alpha k square. You see, you can define a k set of the index of this Hermite basis. Okay. So this gives you a probability measure where the probability of k is alpha k square by variance of f. Right? This gives you a formal probability measure. And I can take the expectation of some quantity with respect to this probability measure. And it turns out that that quantity in some sense has to do with how fast the correlation decays as you infuse new noise in the system.
Thank you.
And again, somehow the dynamical formula for variance is a very quick sort of consequence of expanding in the spectral expansion.
Any other questions?
So this harmonic formula basically comes in developing those dynamical variance formulas. Like,
Oh, this? No, you can use this. No, this is, you can do this with any function. Right? Any function you can expand in the Fourier basis, and then you can use this to get the dynamical formula for variance.
I see.
Well, there are also other ways to prove it, but yeah, this is one.
So in your proof, that's where it essentially comes.
Yeah, so we just use the dynamical formula for variance as an input and then sort of derive the consequences. And so somehow that was derived in this sort of work by Chatterjee using all of these techniques.
And my second question is, when you have this large excursion argument, so you pick the random points from future geodesic.
Yeah.
So as you said, you need to develop estimates uniformly in time.
Not uniform in time, because somehow the time is actually fixed. It's some fixed time at time, some fixed time less than n to the minus 1/3. All if I mean, like when I said uniform in space and time, I meant time in the set of 1+1 sense. So you uniform in two-dimensional space.
Okay, so you can still do that.
Yeah.
Okay.
Here it is. Yeah, exactly. Yeah.
So just to make sure I understand your results right, do they apply both to the Brownian jump model and also to that discrete model where it's
Just the Brownian model.
just the Brownian model? Okay.
But now there's more technology for the discrete models where maybe some of these arguments can be pushed. I mean, like you see that this this thing that I just said, this thing being locally Brownian, this weight profile, which then allows us to do this two-sided thing, and then somehow we reduce it to a question where this is sort of a Brownian-like object which is maximized here, and this is a place which is somewhat far away from the location of the maxima, but Brownian motion is still close to the value of its maxima here. So you need strong comparison estimates to Brownian motion for sort of to make these computations. And so these are at the time of the paper, these were only available for this model of Brownian LPP. Subsequently, there have been more results in slightly more discrete settings, and presumably some of these things can be pushed through. But broadly, this is sort of the thing. I'm like, if you have something like this, then you can make the argument work.
So what assumptions do you think, if you were to try to extend this argument to the fully discrete model, what assumptions on the distribution?
Like, I mean, like this, if you have some comparison to a random walk, that would be something that would be useful to, yeah. So again, like, so the point is you need some understanding of how the weight profile away from the maxima decays. I mean, that's itself is an assumption, but like what assumption on the weight variables will allow you to prove this is sort of course, it's very hard. But for all the integrable models, it turns out that you can actually prove some random walk-like structure for this weight profile, and that should sort of suffice depending on how strong a comparison you have.
So let's thank Shirshendu again.